Okay, we're in business. Last time we were talking about vector fields, and again, there's some bunch of stuff in section 3.4 that I've already kind of talked about. It's pretty premature. All right, we're actually going to be developing the tools needed to really understand what we're doing in 3.4 in chapters 6 and 7. Right, so this is pretty premature. There are some other facts that are mentioned about divergence and curl in section 3.4. I want to give you just I want to lay a little bit of groundwork myself. So this is more stuff that we don't really have the context to really make sense out of why these things are true yet. But again, the book does it, and so I want to give you my context for it. For reasons that I'm not going to be able to tell you, just the way stuff comes together, it turns out that it actually makes really great sense to compose these operators in this order. So specifically, remember that we have this gradient operator that takes functions and gives you a vector field, right? Then we have the curl operator that takes a vector field and gives you another vector field. And we have the divergence operator that takes a vector field and gives you a function. So there are three separate operators, but if you compose them together like this, shockingly interesting things happen. And again, for very good reasons that are well beyond this course and that I'm not going to be able to tell you. But I am going to be able to tell you the cool things that happen. So, for example, the curl of a gradient is always 0. Now, notice on the diagram, that says that we're going to start with some function. We're going to take its gradient to get a vector field whose curl we will then compute, and the claim is that you always get 0. So that's kind of neato. You always get 0? Wow, what are the odds? It's it's got to be useful for something. Here's another one. If you have a vector field whose divergence is 0, and there's some regularity requirements here that I don't want to get bogged down in. If the divergence of a vector field is 0, then that vector field is itself a curl of something. So back up to the diagram. If you have a vector field and the divergence is 0, then that vector field is the curl of some other vector field. So, weird facts, but notice they kind of fit together on the diagram in terms of successive operations in this little composition sequence that we have. So, I like to take all of these, and by the way, there's more than this. These are not the only two cool such facts. There's a bunch of them, and I like to describe them all together with a certain metaphor. That, to my knowledge, I may have made up. I don't know. It's a little bit dark, but it totally makes sense to me, and I find it pretty natural. The mathematical way to say this is that this is an exact sequence, but that's a term that we're not going to have time to fully flesh out. But the big idea is that if you define something called a lifetime, then lifetime will always equal to 2. Now, let me tell you what I mean by a lifetime. If you have a vector field, and then if you take the curl of it, that gives you another vector field. I'm going to view this as being the passage of 1 unit of time. So think of each step along the way as being 1 unit of time. It's just a metaphor. Let me further notice, if you have a vector field and if you take the curl and if you get 0, well, what happens when you take the divergence of that? Well, still 0. Right? And if there was another arrow over here, what would happen if you plug in 0? It's still 0, right? So 0 is this nothingness from which there is no return. This is where it gets a little dark. And if I like to view that as death. Right? If you will. Right? Again, it's just a metaphor. Okay. When you have a vector field, that vector field may possibly actually be the gradient of some function. That's possible, right? It is also possible, however, that there is no function whose gradient is that vector field. So if this is the case, if you have a vector field and it's just not the gradient of anything, it's just not. There is no function whose gradient is that vector field. Then I'm going to say, well, look, this vector field here, we can talk about where it goes subsequently and, what happens there, and then we can talk about what happens there, but there was no sort of prior existence. Because there is no anti-gradient, you might call it, right? Then I'm going to say that this was born here, right? So we have this notion of time, we have this notion of birth, we have this notion of death, right? And that defines a lifetime. And so when we say all lifetimes are 2, now you know what I'm talking about. All lifetimes are 2. So for example, if you have a function and you take its gradient, and then you take the curl of that, well, wait, hey, whoa. All lifetimes are 2. That's 2 right there. So this function, you take its gradient, you take its curl, it has to have a lifetime of 2. That means it dies here. That means that this curl is 0. So this is, again, it's just a metaphor for kind of encompassing these various different facts. This is how this, the curl of a gradient equals 0 is a special case of my metaphorical statement, all lifetimes are 2. Is everybody on board? Furthermore, if you take the divergence and if you get 0, whoa, hey, wait a second, that means that's dying here. Well, if it dies here and if the lifetime is 2, that means it must have been born over here. And that means that the vector field you started with must be the curl of something. Right? So again, that reproduces this statement right here. And there's several others, right? It's any statement about lifetimes that you can get from sort of looking at this this diagram with that metaphor. So anyway, there's much more to say about this. We will do so in chapters 6 and 7. But I wanted to plant this thought. I needed to talk about these facts anyway, because they're in the book in section 3.4. And I wanted to talk about this now because I wanted to plant this idea of composing these operators so that when we get to chapters 6 and 7, maybe, hopefully, you'll think in those terms. Okay, much more to say, yes.
Is there an easy way to prove that there's like an anti-gradient to an existing function?
Yes, there's a method for that, and we'll talk about it in chapters. It's either 6 or 7, I forget. Yeah, yep, absolutely. Okay, so lots more to say. There's lots more relationships between divergence and curl and gradient, and another one that we haven't mentioned yet. And the rest of this is going to wait till chapter 6 and 7. Okay, all right, done with chapter 3. Moving on now. You'll notice we're skipping chapter 4 for the moment. You may have already noticed that on the lecture schedule. The reason for this is that chapters 6 and 7 are challenging. Chapters 6 and 7 are really, I think, the most challenging material in the course. It's very... well, anyway, it's beautiful math, but it's also, there's lots of relationships, lots of connections, lots of ideas, lots of pictures, lots of geometry. There's just a lot going on in chapters 6 and 7. I think that it's best to get to chapters 6 and 7 as soon as possible. I would do it on the first day of class, except you can't. Because you can't do chapters 6 and 7 without certain prerequisites. You can't talk about chapters 6 and 7 without understanding what gradients are. And eventually we're going to need to talk about what integrals are, which is what chapter 5 is about. And it's all about vectors and stuff. So we really need chapter 1. It turns out that the only material in the course that isn't essential prerequisite for chapters 6 and 7, and thus has to go before chapters 6 and 7, the only exception is chapter 4. So I put off chapter 4 because it's the only thing I can. It's the only thing I can delay. And therefore allowing me to get to chapter 6 and 7 as fast as possible. Okay, so that you can have as much time as possible to digest it. All right, so skipping forward, going on to chapter 5. So I'm going to remind y'all that when we were in chapter 3, we started with partial derivatives, and the very first thing that I did is I kind of trash talked partial derivatives a little bit, right? Just a little bit. I mean, they're useful. They're very useful. They're extremely useful. Can't do math without them, but they're not really the fundamental way that you should think about derivatives, right? And we can look back on that at this point and say, oh yeah, because we have the derivative matrix. We have the gradient vector, right? These things are much more fundamentally doing, in a vector sense, what derivatives are supposed to do. And partial derivatives are a kind of a naive first cut that, again, have their uses, no doubt, but we did it first because they're kind of the easiest sort of things to do. So we're going to do the same thing here now with chapter 5. I'm going to start with a point of view on integrals that's really very much not the best. So please do not hang your hat on this point of view. This is just think of this as a preliminary, kind of naive approach that we're going to replace with something much more powerful in just a few minutes. Okay, so here it is. Y'all remember these kinds of problems here, where you take an area, right, and you rotate, let's say, around the x-axis. When you rotate around the x-axis, you get this volume, and the question is, how much volume is that? Right? Y'all remember all these from Calc 1, Calc 2, somewhere along in there? So the big idea is you chop them up into little pieces. Here's a little piece of volume. And the idea then is that you add up from A to B, you add up all of those little pieces of volume, and that gives you the total volume, right? Big picture strategy. Now how much volume is there in this piece, which I'm blowing up here? Well, the amount of volume in that piece is not too hard to see, is going to be the cross-sectional area times the thickness, and that thickness here, this width, you might say, is dx. Okay, so I hope that all looks familiar. So here's the thing, the thing that makes this work, the foot in the door that allows us to be able to do this, is that when we get to looking at that cross-sectional area, what's a circle? Well, it's a disc, but it's a garden variety, barnyard variety, known geometric object, and we just know instantly how to write down its area, right? Okay, so that was a lucky break. Whatever would we have done if that had not worked out? And there's different versions of it. Maybe instead of a rotation, maybe you have a weird shape whose cross sections are all triangles. They're all equilateral triangles, or maybe they're all squares, right? And y'all have all done single variable calculus problems of those sorts. But the cross sections have been discs, squares, triangles, and such. Okay. So here's the harder problem. Suppose I have just not a rotated thing, not something that's defined by convenient cross sections, but suppose I just have a surface here, and I want to talk about the volume under, sitting above the xy plane. I want to talk about the volume under that graph specifically. How would I compute that volume? And can I do something kind of like how here I computed this volume? Can I look at cross sections and sort of take it from there? And, well, bad news, good news. The bad news is that my cross sections are not easy to understand. Right? That cross section is not a disc. It's not a square. It's not an equilateral triangle. It's just not a garden variety, known geometric formula, and so there's a temptation to do what we would do in a single variable calculus class and just throw up our hands and say, look, we're dead in the water. That's not a thing. I don't know I can't just write down an area formula for that. And so the process dies. That's the bad news. Here's the good news. It doesn't have to die. This does not have to be a garden variety high school geometry known area. I can instead just say, well, yeah, but it's still the area under a curve. This area right there is the area under that curve. That curve being, well, the curve that you get when you take the original graph that we're looking at, right? And then we fix a value of y. Only look at this one value of y. Look at that, in other words, at that cross section, that y cross section, you might say, of our surface. And so this purple curve, the area under which we want to know, is described by this equation. Z is a function of x. I mean, okay, technically a function of x and y, but y is a constant. Right? So really, what we're looking at here is, so again, y is fixed, not allowed to change for the purposes of this part of the calculation. So y being a constant, what we have is height as a function of x, and the area under the curve, I can just write it down, and here it is. Let me just shade this a little bit better. This area here, area under that curve, is, boom, it's integral of the function whose graph you're looking at. Don't forget now, mind you, this looks weird. It looks like we've got a function of two variables here. That's an illusion. We do not, because y is fixed. Y is a constant. And so for the purposes of this integral, as we're computing this area for a given value of y, aka a fixed value of y is, we already said it, fixed. So this is a function of one variable. And area under a curve, boom. Right? This is Calc 1, really. I mean, the setup and viewing of where this comes from, sure, that's higher dimensional, but this area under curve as an integral is Calc 1. How we doing? Yeah.
Does it matter whether or not you fix y first, or could you also...
Yeah, great question. We're going to get to that in a few minutes. For the moment, I just want to focus on this setup. Yeah. I'll totally get to that. Yeah. So, yeah, area under a curve. And that means that if I want to look at the, let's see here. Let me go back up to here. If I want to compute, I got so many colors going on here. If I want to compute this volume here, this little piece of volume dV, what is that? This little piece of volume, the pieces of which I'm going to add up over, all the different values from C to D to get the total volume. That volume is just area times thickness. We just agreed that area is that integral. So when I say volume is area times thickness, I get that. And I'm just going to add up those, area times thickness. Again, here it is, area times thickness. And what I have is that I am taking an integral. You see here I'm taking a y integral of a cross-sectional area, which is itself an x integral. We have an integral of an integral. Anybody see how those pieces fit together there? Okay. So it's really, look, it's just like this calculation here. It's volume is an integral of area, but instead of saying area is garden variety, known high school geometry form, now we just have to say that area itself, also an integral, and thus integral of an integral. So because it's an integral of an integral, we call this term here, call this an iterated integral. Here we go. Volume computed here with an iterated integral, because it's an integral of an integral. Side note, I've always been a little uncomfortable with this term. To me, the word iterated means you're doing the same thing twice. I do think it's important to notice that we're not doing the same thing twice here. We're doing a y integral of an x integral. Those are different, right? I try to popularize the term nested integrals, because it really is an integral inside of an integral. So who knows? Maybe that'll take off. But most of the world uses the term iterated integral. So okay, all right. So got to be careful a little bit with what's going on here. Do notice that we cannot start by saying, okay, step one, let's evaluate the y integral. I can't evaluate the y integral yet. I don't even know what its integrand is. Its integrand is the x integral that I apparently haven't computed yet. So you can't start with the y integral. You have to start by computing the x integral. Right? So you have to evaluate what I'm going to call the inside integral first. You can't start with the outside integral. But in the development of the integral in the first place, the very first thing that I wrote down was that we needed a y integral, and then we computed the integrand as the x integral. So in the development, the y integral is first. In the computation, the x integral is first. And the problem there is that if you talk about these two integrals as one of them is the first integral and the other is the second, it's really ambiguous. So please don't refer to either of these integrals as being the first or the second, because it's not clear what that means. Right? What is clear is that this one's on the inside and this one's on the outside. So something you have to be careful with. Keep in mind as well, now it's tempting, again, to look at this inside integral and think that you have a function of two variables. Again, very importantly, you don't. We've already talked about this part, that y is fixed and therefore to be treated as a constant for the purposes of the inside integral there. Well, another way to say this, notice, y is the outside variable. So, however you slice it, and to answer your question, yes, you can do it the other way, and there's, sure. Whichever way you do it, though, the outside variable is constant for the purposes of computing the inside integral. So, as you're on the inside, the outside variable is constant. Is everybody on board? Okay, and again, all from the picture. All right, so let's do one. And we've got a graph here. Of course, y'all recognize that graph. That graph is a paraboloid, right? Flashbacks to chapter 2. And if I want to compute the volume under that graph, well, we just got through deriving a formula for how to compute the volume under a graph. Again, here's the volume under a graph. What we've been talking about here. So I don't have to slice or anything. I can just immediately write down the volume under the graph is this iterated integral. And it's just set up exactly like we have it above as applied to this particular graph. Now, there's a couple of little details that do have to be pounded out here. A couple of landmines. I want to warn you all of the landmines. I mean, the broad stroke is easy. The broad stroke is evaluate the inside integral. It's a single variable calculus problem. Crank it out. Once you've got that, then you've got a single variable calculus problem to do the outside integral. Crank it out. I mean, the broad stroke is just plug and chug. Here's the landmines. First landmine. This term right here. Very tempting to look at that and say, oh, yeah, I know how to do integrals of when you have something squared, you get 1/3 of that something cubed. Very tempting. Very tempting. A lot of students step on this landmine. Don't forget, though, that's the outside variable, right? We are working on the inside integral. Therefore, the outside variable is a constant, and therefore y is a constant. Therefore, y squared is a constant. And the way you take an integral of a constant is, you use constant times whatever the variable is. The actual variable here is x. The antiderivative of constant is constant times x. Everybody good? So heads up, this is part of your responsibility as a student to, evaluating an integral is to remember which variable is a constant and which variable is actually a variable for the purposes of what you're doing. Okay, so careful with that landmine. Here's the second landmine. Got your antiderivative here. There you go. And we're going to take the values. By the way, let's see. X goes from 0 to 1. You can see right here, x goes from 0 to 1 from the picture there. Right, so the range of values of x is 0 to 1. And it's very tempting to just write down 0 and 1 and to just start plugging those in. And here's the problem. What will happen is students will take, for example, this value 1, we'll plug it in there, and we'll plug it in there, and then kind of forget where they are and what they're doing, and then inappropriately, but sort of, understandably, plug it in for y also. And that's not a value of y. It's a value of x. Right? So the solution to that problem, in my opinion, this is just how I do it, is I don't just recopy the 0 and the 1. Because then it'd be easy to forget that these are values specifically of x. Right? So what I do is I write x equals 0 to x equals 1, and that's my visual reminder that these get plugged in for x, full stop. They do not get plugged in for y. No, of course not. That's not y. Y is a constant. It's not the variable. Is that cool? Does everybody see my motivation? Okay. All right, that's not required, but again, this is just advice, but I think this is really good advice, and I hope you all will take the extra second and a half to spare yourself oopses that'll cost you. Okay. All right. So the rest of it is algebra. Notice that in the evaluation of this inside integral, because we're treating y as a constant, what we end up with that turning into is here we are. A function of y. Said differently, there's y's left over in this expression. Why are there y's left over? Because I didn't do anything to them. I didn't plug them in for other values. They aren't other values. They're constants, so the y's remain. Now, for the purposes of the outside integral, as y goes from 1 to 2, now y is a variable. Right? It's a little bit weird. For the purposes of the inside integral, y is a constant. But now for the purposes of the outside integral, as we are moving in the y direction, looking at not just at one slice, but looking at successions of slices and seeing how those slices add up. Y is the variable, and so now the antiderivative of y squared is indeed 1/3 y cubed, because y is the variable. Yeah?
Just a small detail.
Yep.
Are we guaranteed that the coordinates for the rectangle will always be x coordinates followed by y?
Nope. I'm gonna same as the question he asked a minute ago. You can slice in the other direction, and it's kind of a fielder's choice. And we'll talk about that in the very next thing. Yep. It's a good question. Okay. All right, and then algebra, and then plugging in, and arithmetic, and y'all can do the rest. It's literally single variable calculus. Okay. So exactly to your question and to your question. You can just slice the other way, and it's perfectly fine. Notice that what we did in this initial picture is I arbitrarily, no good reason, decided to take this loaf of bread here, right, and slice perpendicular to the y-axis. There's no particular reason why I had to do it that way. I could just as well say, hey, let's slice perpendicular to the x-axis. The slices will then look like this. Right? I have a bunch of slices like that. And I could talk about how those add up. And I could ask, how can I compute this cross-sectional area? And I could talk about how that's an integral in the y direction, for which x is a constant, etc. Right? And I'm going to leave these details as an exercise to y'all, because again, we have it fully fleshed out in complete detail here going this way. And I want you to think about how would this argument get adapted? How would the picture change? What happens to the A's and the B's and the C's and the D's? And just think through how you can take all the same ideas, turn them sideways, and conclude. I claim you would conclude that the volume instead could be written like this. And you'll note here we have X on the outside and Y on the inside. As opposed to what we derived previously, which is that the volume is an integral with Y on the outside and X on the inside. Okay, and of course you'll notice very conveniently that what happened here was kind of this deal, right? So the outside bounds and the outside differential just become the inside bound and the inside differential. And likewise, the insides become the outsides. So you get this phenomenon right here, right? Very convenient. And just one heads up about that. This is a peculiarity of the fact that our domain is a rectangle. Let me go back to the picture here. This is a peculiarity, of the fact that I'm trying to find the volume sitting over a rectangle. And if this shape is anything other than a rectangle, we don't yet know how to do that, right? But we will soon. And when we get to that point, you get to forget about all this. This business right here does not work. Having a rectangular domain is the only time when this happens. Okay. Alrighty. So here's the next natural thing you might want to do. Recall in single variable calculus, we computed all sorts of stuff. We didn't just compute area under a graph. Right? So we computed mass of a one-dimensional rod, the population of bacteria, the amount of work that it takes to whatever. Right? Lots of applications. So let's try to play out, can we do those by analogy as well? Can I use this idea of an iterated integral to answer this seemingly analogous question to an old single variable question? So instead of having mass distributed across a length in the form of having let's say a metal rod, right? What if you had a two-dimensional rectangular sheet where we have mass distributed across area, right? So mass per unit area is the form of density that we're interested in. If I know the mass per unit area, can I compute the total mass? And it's tempting to say, oh, well, an iterated integral worked for computing volumes in single variable, areas in single variable and then volumes in multivariable. Yeah, you'd think that it ought to work for computing masses and such as well. Let's think it through. At the core of the iterated integral argument that we just made, we were multiplying height times length, right? That's where the f and the dx came from. The f is a height, the dx is a little distance in the x direction, and that gives us a little area of a strip, right? So, and then we add that up and interpret that as an integrand, and blah blah. It goes from there. But that, in some sense, the first part of the calculation is to interpret that integrand times dx is height times length. And we understand what that is. That's area. And furthermore, and really importantly, I know stuff about area. I know that area does what I'm going to call accumulating. Area, right? If you have a little piece of area here, and then you have a little piece of area right next to it, this area plus that area gives you the area of the whole. So that's something that area does. And I want to point out, not every quantity of interest does this. Nice example is concentration. Right? So if you have a glass of water that's, 10% salt, and you have another glass of water that's 20% salt, if you mix them together, is it 30% salt? No. It's something in between 10 and 20, and it does not just add like area does. Right? So there's two important tools that we use at this stage of this initial calculation. The very first little bit of calculation is something that we understand, and furthermore, that thing that we understand has this critical feature of accumulation. Now let's keep that in mind as we try to do the same thing with masses and such. I mean, this is kind of what you would expect the answer to be, right? So, okay, well, what is this? Well, I've got density times length, but don't forget the density is mass per unit area. So this very first, sort of the nugget, the very first thing that I have to do in this calculation, I've got to figure out what is mass per unit area times length. And that's kind of a mismatch, right? Mass per unit area, the whole idea is you're supposed to multiply it by areas to get mass. So multiplying it by a length, this is not its intended purpose. It's not that I can't figure out what it means, it's that I've got a problem to try to figure out what it means. And then it's worse than that, because you could take a unit's point of view and say, well, mass per unit area times wouldn't that give you mass per unit width or something like that? But that's a units argument. What is that thing? Does it accumulate like area does, or does it not accumulate like concentration does? Doesn't. Well, again, it's not that there aren't answers to these questions. It's that these are non-trivial questions. Right? So we've got a problem, not knowing what we have, not knowing whether it has the critical feature of accumulation, and so I don't know if the rest of this actually even makes sense at all. And I'm going to say we're dead in the water. So this is a problem. This is one of the reasons I'm not a huge fan of iterated integrals. I think they serve an initial purpose. Yeah, we got to answer that. Volume under a graph. That's nice, right? But that's about it for iterated integrals. And we need a better tool that will not crash and burn like this did. Okay, and here it is. Something called a double integral. So this is not to be confused with an iterated integral. It's a different thing from an iterated integral. It is a natural sort of extension of the idea of a single variable Riemann sum. And I just want to real quick make sure that everybody knows, what a single variable Riemann sum is. A lot of y'all have seen this right here, and you've seen this expression, this Riemann sum, and there's a bunch of little detailed trappings that come along with it. And in a lot of high schools, it's presented as, you don't need to worry about this part. We're never going to use this to evaluate integrals. We have the fundamental theorem of calculus to evaluate integrals. And that's true. And in practice, nobody actually computes with these things. That is a red herring. That's not why we have Riemann sums in the first place. The purpose of a Riemann sum is not to compute integrals. The purpose of a Riemann sum is to define integrals and to allow us to connect integrals to other things. So in particular, if you want to compute a mass of something, a lot of high schools would say, we want to think of mass as being an area, and then we'll compute the area as an integral with the fundamental theorem of calculus. This is how it gets presented in a lot of high schools. And I claim that doesn't make any sense at all. As an argument, how exactly can I confidently interpret a mass as an area? Those are different things. Right? If I look at I've got a one-dimensional rod, I've got, here's my x-axis, and I've got a rod like this, sitting along the x-axis, and I want to compute the mass there. Where in this picture is there an area? There's no area. So we're kind of making stuff up if I say, mass is just automatically area. Now, you can make a stronger argument, and you can say, well, the thing is I can compute mass by chopping it up into little pieces, and exactly how you flesh in the details of that argument depends on how precise you want to get. But the more meaningful and precise you are, what you're really doing is saying I can compute mass with a Riemann sum, and that Riemann sum also computes an area. So yeah, sure, you could make that connection by way of a Riemann sum, ultimately. And the more you avoid using a Riemann sum in this argument, then the more sloppy and meaningless the argument is. Fundamentally, it is a Riemann sum. You're taking something, you're breaking it up into little pieces, and you're adding those up. That's what a Riemann sum is. So, you look at this picture then. Why would I make this argument, right? When instead, much better, I could just make this argument. I don't need area. You don't need area at all to compute the mass of a rod. Mass is computed with a Riemann sum, aka an integral, and we compute integrals with the fundamental theorem. Done. No area. Is everybody good? All right. There's a lot more to say about integrals. A lot of people, again, have these what I think are bad ideas from high school that just sweep important details under the rug because it's high school. What do you expect? I think it's important to get all that straightened out. If some of this is news to you, or if you're maybe a little uncomfortable with Riemann sums and what are Riemann sums good for and how is it that Riemann sums are the connection to a huge number of applications? I have a tool for you. I hope this might be useful. It's a recording that I recorded several years ago at this point, but what is an integral? It's right here on my YouTube channel, Miscellaneous Topics playlist. Give it a look. It's a half hour. I addressed 3 common misunderstandings about integrals. And I think it's stuff that every multivariable calculus student should know. It's really stuff every single variable calculus student should know, but certainly in this class as well. So give that a look if you feel like you might have a need for that. Whoops. Here we go. Okay, so what we're going to do now, with the understanding that integrals are Riemann sums, and that Riemann sums are what allow me to connect to applications, we're going to try to come up with a 2-dimensional version of this. And really, we're going to kind of do all the same things that we did with single variable Riemann sums. We're just going to add a bunch of stuff up, except instead of adding up over an interval, we're going to add up over a rectangle. So instead of taking an interval and chopping it up into a bunch of little pieces, and on each piece writing down, an expression like this for whatever reason, depending on your application, and then just adding them up. We're instead going to chop up the entire rectangle. And so here's a rectangle, and I'm going to chop it up like this. There's some details that we'll get to in a minute. We're going to chop up like that, and then we're going to keep chopping horizontally as well. It's harder to draw these straight lines than it looks. Chop it up in both directions. Right? We're going to get a bunch of little pieces, not just in little pieces. We're going to have in squared little pieces. And then on each piece, we're going to do like we did below. We're going to multiply the value of some function times the size of that piece. Right? That's the exact same thing that we did here on each little piece. Value of some function times the size of that piece, the size being delta x. Now let me remind you, why would we do such a thing? Why in single variable calculus did we create this structure where we can multiply some arbitrary function times size? And it's because there were so many circumstances where we needed to multiply something times size. If you're computing an area, you want to multiply height times this size, aka this width. Height times that width gives you little pieces of area. If you're computing the mass of a rod, well, then we have mass per unit length. This would then be a density, mass per unit length, that we would multiply by lengths to get little pieces of mass, which again, then I can just add them up, right? And we're going to do the same thing over here. We're going to say, all right, well, we've got this rectangle, and maybe for whatever reason, I might need to multiply some function times the size. Maybe I'm computing the volume under some graph surface, in which case I would need height times area to give me little slices of volume that then add up to give me the total volume. Or I'm going to the previous example where we kind of crashed and burned here. Right? So we crashed and burned when we were looking at a rectangular sheet where the density was just, the mass was distributed across area. So we have mass per unit area. And well, okay, if you have mass per unit area, fine. Mass per unit area times area, mass. No funny business. No, what is this thing? How does it behave? No, mass per unit area is a concept made specifically to multiply by area, with the understanding that that means that would give you mass, and little pieces of mass add up to the total mass. How we doing? Is everybody on board so far? Yes.
So, does this Riemann sign give you volume or area?
It depends on your question. If your question is that you want to compute the volume under a graph surface, and if you make this the function whose graph you're looking at, then it gives you volume.
Okay.
Right? If you are computing the amount of mass in this rectangular sheet of metal, and if the F represents mass per unit area, then you get the total mass. So this expression computes, in some sense, kind of whatever you want it to do. It depends on the application. Just like single variable integrals, what does a single variable Riemann sum compute? Well, if you're interested in area under a curve, okay, then just make this the function whose graph you're looking at. If you want to compute the mass of a metal rod, then this is mass per unit length. If you want to compute the number of bacteria, blah blah, the different details in every application. The point is that this is a way for adding up accumulating quantities that accumulate over a length. This is just a way of adding up accumulating quantities that accumulate over an area.
So this is kind of like a cross section of.
No. This could be lots of different things. Why I have drawn a rectangle here and what it is that I want to add up over that rectangle. I don't know. Maybe it's mass, maybe it's volume, maybe it's bacteria.
I don't really see how this is different than what we were doing before, because you're just doing delta x times delta y, which isn't that just like the size of your rectangle?
It is, but there were no rectangles in my initial argument here. In my initial argument, I was taking a single variable integral, right, where I'm taking something that's mass per unit length and multiplying it by, mass per unit area and multiplying it by length. And that was a mismatch. That was in some sense the problem here is that I didn't have an area to multiply it by. Does that make sense? Yeah. Cool. Okay, so this is called a double integral. This expression from the previous page is a double integral. We have this notation for it. I think the notation's pretty reasonable. Delta x times delta y. In some sense that represents the area of our little chunk of rectangle. And so dA, I think, is a pretty reasonable notation for it. It's just a shorthand, honestly. But I think it's a reasonable shorthand, given that it represents a little piece of area. And as usual, we take all of this business and we call that an integral. Just keep in mind, I'm having to add up in two directions here, because I'm not just adding up. Let's see here, my picture's gotten a little out of hand. Let me clean this up. I'm not just adding up in one direction like that, right? I'm adding up in that direction, and then I have to do the same for each value of y. So I'm adding up in two directions, right? And so now this is, again, it's just notation. It's arbitrary, but because I'm adding up in two directions, we're going to use two little integral symbols. Think of this as a single thing. This is a single symbol called the double integral symbol. Not to be confused with a single variable integral of a single variable integral. This is a brand new thing that represents this two-index, two-direction summation. Is everybody good? Okay. All right, now a little bit of formalities. The book does some highly commendable discussions of additional formalities that go to making this even more rigorous and even more mathematically robust and powerful and capable in situations that we're not going to have to see, that we don't have to worry about. Every function that we're going to deal with is continuous. And for continuous functions, all that extra stuff that the book does doesn't make any difference at all. And so this, for the purposes of Math 219, we're going to ignore all that stuff. So in particular, the book spends a little time talking about irregular partitions and test points, and just don't even worry about that at all. You're excused. You don't need to. We're not going to mess with that. Okay. So as a first example, notice we can compute the volume under a graph with a double integral. So there's that. Now we've already done that. We've already computed the volume under a graph. We did it with an iterated integral. But I'm going to do it now with a double integral. That volume I can view as saying, well, let's look at one little piece of area at a time. For each little piece of area, the area times the height, right? Area times height gives you the volume of that little piece. Right, this little French fry here, right? That the volume of that French fry is height times the area of the base, boom, and then I just have to argue that the total volume is what you get when you add that up. We're going to add that up over all of the rectangle, and that's a, you'll notice this expression here. This expression here is exactly a double integral. Okay, I'm out of time. I'm sorry. So we'll pick up here on Friday. By the way, the grading of the exam is proceeding. I've got 3 of the 5 pages done. Hopefully, we'll finish tomorrow. That's the plan. So, see y'all later.